We present motion-aware event suppression for event cameras. When navigating a dynamic environment like autonomous driving, a system faces a fundamental challenge, separating our own movement from the movement of others. As you can see here, the camera's own ego motion causes the entire static background to shift in the frame. At the same time, we have independently moving objects, like these other cars, following their own trajectories. For event cameras, this combination creates a severe bottleneck. While incredibly powerful for fast-moving robots, they respond to any change in the scene. They trigger events equally from the background ego motion and from the independently moving objects. However, as is visible in the scene, only a small fraction of the data actually belongs to the moving objects. In this visualization, the green events are associated with the independently moving objects, while all the white events are generated by ego motion. Because event cameras cannot natively distinguish between the two, this creates a massive undifferentiated flood of data that easily overloads downstream systems. As can be seen here, current approaches struggle to handle this efficiently. Most methods either rely on computationally heavy, dense scene reconstructions that introduce significant latency, or they fall back on brittle, hand-tuned filters that require constant manual tweaking. More importantly, existing algorithms only react to events after they arrive. By the time they finish computing a mask, the objects have already moved, leaving the system lagging behind reality. To solve this, we introduce a lightweight architecture to jointly segment independently moving objects and predict their future motion, enabling anticipatory suppression of dynamic events before they even occur. First, we compress a short temporal window of events into a voxel representation. The network then encodes these voxels using a series of small convolutional GRU blocks and decodes the resulting features to accurately predict the current object masks. Next, we modulate the input features based on a target future time. We do this using our novel Attention-Based Time Conditioning module, which we call ATC, to estimate forward optical flow. Using this optical flow, the mask is warped forward in time so it aligns perfectly with the incoming events. This cleanly separates the independently moving objects from the background. Because we forecast into the future, we successfully compensate for computation time while running at 173 Hz. On the challenging EVIMO benchmark, we compare our method with different baselines for predicting in the future, like EVIMO and OMS. We establish a new state-of-the-art, outperforming the previous best method by 67% in segmentation accuracy while running 53% faster. Our approach remains robust in challenging nonlinear indoor motions like the following. Beyond indoor scenes, our pipeline seamlessly scales to the complexities of real-world autonomous driving. As you can see in this sequence from the DSEC dataset, our anticipatory mechanism successfully isolates vehicles amidst heavy background clutter. It handles the high-speed ego motion of the car, accurately anticipating the movement of vehicles further down the road. But the true value of event suppression is how it enhances downstream perception tasks. By providing a clean, decoupled event stream, we dramatically reduce computational load. For example, by using our dynamic masks to guide token pruning in vision transformers, we accelerated inference speed about 10 frames per second with a negligible drop in accuracy. Our code and models are fully open source. Scan the code for more information. Thank you.